So now that you've had a chance to learn a little bit about how parallel streams work, let's give a quick summary of where things can go awry with parallel streams. Now, if you recall, we had talked earlier of where things could go awry with concurrency and parallelism in general. And no surprise, a lot of the things that can go awry for parallel streams are very similar to the things that go awry for concurrency and parallelism in general. And it usually boils down to the root of all evil, which is shared mutable state. So that's usually where things start to get problematic. So if you play your cards right and you have workloads that partition nicely without sharing anything, then ideally the output of a behavior in a stream, that's this little thing here, behavior F, for example, it should only depend on its input arguments. In other words, there shouldn't be any side effects, ideally. That doesn't always hold, but sometimes often you can make that the case. So here's a very simple example of a behavior that only depends on its input. This is the capitalize method we looked at before. We used that as part of the Hamlet example. And as you can see here, we take a string S, and if the length of S is 0, we return S because it's kind of a no-op string. Otherwise, we take a substring, which is the first element in S, and we uppercase it, and then we go ahead and take the rest of the substring, which is from skipping over the first element, and we lowercase that. So you can see here there's no side effect. Takes the input, works in the input, returns the output. That's something that's often referred to as a pure function or a side effect-free function. If you don't follow that type of a design, if you have things with side effects, then you can end up with race conditions. And if you recall, race conditions are this weird problem that arise in software when an application, in this case the stream, depends on the sequence or the timing of its threads in order for it to operate properly. What that's really saying is, if you get lucky, then you're going to end up in a situation where things appear to work, but of course, you're often unlucky, and then your behavior, your programs will fail because it depends on stuff that doesn't always go your way. And it's kind of Murphy's Law, first rule or second rule or third rule of computer science is things will always go awry at the worst possible time, like when you're doing a demo for a customer or when you've got a very important workload that you can't get wrong. That's when these problems will sneak out and bite you. So let's take a look at an example that demonstrates this particular problem. Let's show an example that's incorrect. It's a buggy way of implementing a factorial method in parallel. So we're going to use parallel streams, but we're going to do it wrong. And you can find this example here in the EX16 folder. It's really fun to run this one and see what it does, because you can see very quickly it goes awry. Because I also have implementations that work properly in this test case too. So here's the factorial. We give it n, and it's supposed to return the nth factorial. By the way, just a side note, if you know much about the growth rate of factorials, if you get an n that's much bigger than 22 or 23, it starts to wrap around because it gets larger than the size of a long. The way to address that is to use a different abstraction called a big integer. And a big integer is a software-defined abstraction in Java that allows you to have infinitely large integers. In this case, we're limited by the size of 64-bit longs. Anyway, that's just a little side note. I have other implementations actually in this test case that demonstrate how to use big integers. So what are we going to do? We're going to make ourselves a local variable called t of type total. And if you look at total, total is a class that has a field called mtotal, which is a long. It's initialized to 1. And it has a multiplication method called mult that multiplies mtotal by n, where n is passed as a parameter to mult. And right away, you should start having big flashing red lights, waving around arms and fireworks going off. This is a problem because this is shared mutable state. Well, at least it's obviously mutable state. It's mutable state because we're modifying it. We're modifying mtotal by multiplying it by n. It's shared mutable state because of the way we're using it in the context of our buggy implementation. And our buggy implementation works as follows. It generates a range of integers from 1 to n, and then it processes everything in parallel. And for each of the values 1 to n, it's going to call mult on that value. Well, the problem here, of course, if this was sequential, it works fine. If it's parallel, then we're having each of these threads modifying m total. And if you look there even cursorily, you'll see that there is, in fact, no synchronization on mult. So this multiplication of m total by n and storing back into m total is an unprotected access of shared mutable state by multiple threads in parallel, and chaos and insanity results. So that's going to be a big problem. And this will then lead to race conditions, and you'll get very strange results. Now, there's all kinds of ways to address this, which we'll talk about later. I will also mention something else just in passing, because it's worth being at least vaguely aware of this. This return of m total with the result here is also going to cause trouble because, once again, this is unprotected state, and so it will not be guaranteed to be pushed through all the processor core caches in any timely manner, if ever. And so you can end up with very strange behavior here as well. So this program is buggy at all kinds of levels. We'll come back later and show how to write it properly, or if you get impatient, you can just go here and look at this EX16 example, because I show correct ways of doing it in there. So in Java, oddly enough, only you can prevent concurrency and parallelism hazards, kind of like Smokey the Bear, right? Only you can prevent forest fires. The compiler will not save you in this case. The Java virtual machine will not save you in this case. You are responsible for recognizing this. Now, the solution is really quite simple. Use parallel streams correctly with the appropriate terminal operations like collect or reduce, and all these problems disappear. So if you follow the very basic rules, then everything will go well. There, of course, are other challenges with parallel programming and so on, but this is probably the most common one. And as always, the shared mutable state being the root of all evil is underlying all these issues.